Good afternoon, ladies and gentlemen. So this video is focused on reviewing the first of the 4 FRQs. We had a Zoom class, at least when I'm recording this, we just had Zoom class where we kind of practiced through it. So this is for those of us who either weren't able to make class or want to watch this again just because they want a little more explanation. So we're looking at FRQ number 1. We're going to look at my answers. There is a scoring guide on Canvas you're welcome to look through. It kind of shows what they're looking for. There's a couple questions on this one that are a little bit strange, so it might be useful to just kind of listen to my explanation. So let's jump right into it. So hopefully you had a chance to work through this. If you haven't, pause this video. You need to at least attempt this FRQ before you listen to me talk about it. All right? So at the beginning, it starts with the idea that these students are carrying out a series of experiments. And in this case, what it is I have 2 blocks, and I'm launching them from the same launcher that causes them both to leave at the same initial velocity, and I'm launching them across a table that has some friction. All right. Now, I have a couple students that are watching this, and they're making a prediction. Now, the first student says that they predict block A is going to slide farther along the table before coming to rest. Now, block A has twice as much mass as block B, and then student 2 says the opposite. They think block B will slide farther. Now, what you are going to do is, in this question, it basically wants you, what the AP graders are looking for, is for you to kind of look into their prediction and give some sort of physics reasons why that might happen. Now, in the AP exam, more than likely to be more specific than this. I actually think this is kind of an open-ended question personally. But that being said, if we look at this first question, they think block A is going to slide farther along the table before coming to rest. Well, let's think about some things that block A might have that block B does not have, or what block A has more of compared to block B, because it might explain why it goes farther. So, if block A has the same velocity, but it's twice as massive as block B, then what that means to us is that actually block A has more momentum than block B does. Now, if you look at the scoring guide, it talks about the idea it has more inertia, so it resists its change in motion more. Inertia in our particular class just means momentum, so it says more momentum. And we talked about the idea that when objects have more momentum, they are more difficult to stop. So my guess is that this individual is going on the idea that block A has more mass, which means it's going to be more difficult to stop. Now for block B, it's kind of going along the same line of thought. Student 2 is looking at the idea that block B is probably less massive, which means if we think about forces, or you could talk about momentum, either one would be fine. If you think about forces, block B probably experiences a weaker force of friction, which means its acceleration might be less. Maybe. We don't know if that's true yet, but that's what we're just thinking here, which means it'll probably take longer for it to stop. These 2 questions are very strange in that they're asking you to basically kind of look into the mind of these students, which is why on the AP exam, more than likely what will happen is the student will say why they made their prediction, and you will have to evaluate if it's right or wrong. Now, part B is asking about a mathematical expression. Now, in this case, these questions are 100%. You will see a question like this in the AP exam. And what it means is it'll ask you to kind of make some predictions. It'll ask you to do a little bit of math, solve maybe one to find a formula, and then it'll ask you to use that formula to make another prediction. In this case, it says to derive a mathematical expression you could use to find the distance traveled by block A. Basically, it wants you to find some formula that could calculate how far would the block slide before it stops. All right? Now, in this case, there are 2 ways to do it. On the score sheet, it only talks about one way, but there's actually 2 different ways. Whenever we talk about something moving and experiencing kind of a constant force, we should immediately think that we can either do energy, that's the first way we could do this, and use the idea of work and energy, or you can use kinematics and forces. Either one is going to be fine, and I actually did it both ways. So let me talk about the energy solution first. If I'm using the idea of energy, what I do is I say the block starts with kinetic energy. When all is said and done, all of that energy has been taken away by friction, and basically it has been removed by the work done by friction. So what we have to do is we have to first write out the formula for kinetic energy, 1/2 times the mass of the block A times how fast it was going squared, and that's going to be equal to the force doing the work, friction, times how far it slides before it stops it. All right? Now in this case, I know the formula for force of friction. We know that it's mu times Fn, and then we know the idea that the force Fn, if we draw an FBD, the normal force is going to be equal to the weight of the block. So if you're wondering where I got this, all I did was replace F of F with the coefficient of friction times the weight of the block. All right. Now, what's interesting is that you'll notice on both sides, I have the mass of the block, and actually I can cancel those out. So MA goes away on either side. And I'm left with, when I solve for delta x, that the distance this thing slides is going to be equal to its initial velocity squared divided by 2 times the stickiness of the surface times the gravity field this thing's moving in. All right. Now, if we do it using kinematics, you can do the exact same setup. However, if I'm going to use kinematics, I start with my chart. I look at what is told to me in the question or what I can assume. I know the starting initial velocity, it's v naught. I know the final velocity is 0. But I don't know anything else. Even though I wrote something in my chart, I actually don't know that yet. It doesn't tell me anything about the acceleration. So what I'll have to do is I'll have to use Newton's second law on forces to calculate the acceleration. Now, I kind of cheated. I did not do what I was supposed to do, which is I need to draw the FBD. And if I do that, all right, the FBD for the block as it's sliding is going to look something like this, where I have Fn up here, Fg, and F of F. Right? Now, because of that, I can see that of the 3 forces, the only one that's actually providing a net force is the force of friction. So to use Newton's second law, I do the net force is equal to the mass times the acceleration. Looking at that, that's exactly what I've done here. Then I just plug in the formula for force of friction, which is mu times the weight of the block is equal to ma. Once again, the masses cancel out, and I'm left with that the acceleration is just equal to a negative mu g. All right. And once I know that, I plug it into the chart. I use some kinematics to solve for delta x, and I get the exact same formula that I did before. Now, besides the fact that this makes sense because these are both the same, it just shows that there are multiple ways to solve a question, and you can get the same amount of points either way. All right. Now, the last piece is part C for this first half of the question. Does your expression you derived, and this is how it's going to be phrased on the AP exam, it'll basically say, does the formula you came up with either support your reasoning, or it'll ask something along the lines of, imagine I changed this, what will happen according to your formula? In this case, it wants us to know, does our formula support the reasoning, what student 1 and student 2 said? And actually, this is part of the reason why I don't like this question a ton either. And of course, I keep saying that. People are probably wondering why I picked this question. It's still a good practice. It's actually suggesting that one of them is right, when in reality, neither one of them is correct. What's going to happen is that student A, and how I phrased it is I basically first acknowledge what they were saying, what part they said that was correct. So I said student A is correct that block A will have more energy or momentum. And student B is correct that block B experiences a lower force of friction. But looking at the actual formula that we calculated for how far something will slide, it actually does not depend at all on the mass of the block. And it doesn't matter if I do this with mass A or mass B, the masses cancel out on both sides. So it's only dependent on how fast I launch it. They both have the same launch velocity. The surface it slides on, they both slide on the same surface. And the gravity field they're moving through, they're both on the same planet. So in fact, these two objects actually slide the same, they're going to go the same distance before they stop. All right? And if you can kind of replicate this at home somehow, you can see that it's probably also going to be pretty true. That's what's going to happen. So, right there, that's the first half of this question. Now, second part, it modifies it slightly. And what it does is it makes it so that now I tie a rope to one of the blocks, and now instead of it going in a straight line, it's going to go into a circle. Now, the first question is it basically wants you to figure out what is the maximum tension in the string during the motion in terms of given variables, and it wants you to justify why you picked what you did. So, for the first one, this is worth 3 points. We identify first what is keeping this going in the circle. And we know if this thing's going in a circle, it must be experiencing a centripetal force, which means that something has to be providing that centripetal force. In this case, it's the rope. And the rope is providing a tension force. So we say Ft equals Fc. Now we have a formula for centripetal force. It's the mass of the object times how fast it's going at that point, divided by the radius of the circle. So the mass of the block, because it's block A, is ma. At the very launch, it's got a launch velocity of v0, and then it's squared, divided by the radius of the circle. Now, a lot of you probably stopped and you just said, oh, right, the radius of the circle is L. The problem is we cannot make that assumption in this question because it says the block has a width of d. Now, what that means is that the block actually has some size. So we actually have to pay attention to where the center of mass of the block is. Because in reality, the laws of physics are governing basically the center of mass. So the circle this thing is following is going to depend on the radius the center of mass makes. That means that the radius is not only the length of the string, but it's also half the distance of the block, or half the width of the block, because the center of mass is right in the middle. So the radius is actually going to be the length of the string plus half the width of the block. All right. And then lastly, once we do that, we can kind of answer the max tension question and part 2 at the same time. Looking at this formula, there are basically 3 things that the tension cares about. It cares about the mass of the object, which if we look at the problem, that never changes. It cares about the radius of the circle, which if we look at this also, the radius stays consistent the whole time. And it cares about the velocity it's traveling at. Now this is the key, because this is still the same setup as before, so there's still friction involved. So as that block slides around in the circle, it actually starts to slow down because there's friction. Because of that, it means that the force of tension actually starts to decrease as the block is moving around the circle, which means the centripetal force is also going to decrease, right? Or what you can really say is vice versa. You can say that the centripetal force is going down because it's going slower, which means the force of tension needed also decreases. That means that the maximum tension, the most tension we need to keep going in the circle, is at the very beginning of the launch, because that's when it's moving the fastest. All right? So right there, this question is kind of 2 parts. What's nice is that the second half actually doesn't really even depend on the first half. So if you're stuck on one part of this question, move to a different part, because more than likely there's going to be a section that's not related to another piece, and you can start kind of doing some work there, and it might jog your memory for the other part. All right? So if you want to, feel free to go through and look at the scoring guide about how you actually get the points for these questions. But that's the end of our kind of analysis of this first FRQ. The next video is going to talk about how to answer FRQ number 2.